We will see now an example concerning one of the type of manipulations we can do to the equilibrium values or reaction coefficient values. We will see that the form of the reaction coefficient or the equilibrium expression depends on the direction in which the balance equation is written. So let's consider the following example where when nitrogen monoxide combines with oxygen to form nitrogen dioxide at 180 degrees Celsius, the equilibrium constant value is provided to you, 1.48 times 10 to the 4. The question is, write the equilibrium constant expression for the forward and reverse reactions, and then calculate the value of the equilibrium constant for the reverse reaction at the same temperature. So let's start writing the equilibrium expression for the forward, but for that we need to write down the chemical equation. Let's start writing the forward reaction provided in this example. Remember that the equilibrium expression or the reaction coefficient depends directly on the coefficients in the chemical reaction, so you have to make sure that not only writing correctly the chemical formulas, but also writing down the coefficients, right? So we have to make sure that equation is balanced. The other thing that is important is that in this case you need to make sure that you write down the physical states of the species in the reaction. We will see that writing the equilibrium expression also depends on the physical state of the reactants and products. So once you have that balanced reaction, we write down the equilibrium expression. In this case, remember that products goes on the top, right? And we have to elevate the concentration of the products individually, right, to the coefficient in the chemical reaction. And then we divide that by the reactants. Again, elevate each of the concentrations at equilibrium to that coefficient. Let's do now the reverse reaction. So now we wrote the equilibrium expression for the reverse reaction. Notice that now the previous products now become reactant and the previous reactants now become products. So notice that even that each equilibrium expression is characteristic for the reaction as is written, you can find a relationship between the two. If you notice, the equilibrium expression for the reverse reaction is actually the reciprocal of the equilibrium expression for the forward reaction. And we can write down this relationship and we can relate both of the constants. Okay, I'm gonna just work it out mathematically so you can see it. So in this statement, it is provided to us that the Kc for the forward, right, Kc of the forward expression, right, or the forward reaction equals to 1.48 times 10 to the 4, okay? So I just told you, right, that we can relate Kc of the reverse as the reciprocal, which is just mathematically what it means is 1 over the Kc value of the forward reaction. Okay, we can actually use this expression to calculate the numerical value of the Kc of the reverse, but I want to prove you right how these two values are related mathematically. So to do that, we are going to expand this. Okay, it's 1 over, right, the expression, the Kc expression that we have here on top of the forward. So I'm going to just write it down. Okay, and it turns out that we have exactly, right, the same expression, okay, as defined by the direction, right, of the chemical equation. So now let's calculate the real value, right, for this problem. So the question was, what is the Kc value of the reverse reaction? And we know that it equals, right, the reciprocal of the Kc for the forward reaction. That means that it's going to be 1.48 times 10 to the 4, right, the reciprocal of that. And in terms of the numbers, that equals to 6.76 times 10 to the minus 5.